So, hello everyone. Uh, Today we'll be seeing about Bayesian inference and Monte Carlo Markov chain. So, in this week challenge, we've been seeing about having a data about analyzing the price of oil and trying to find out in which part or what type of events will make the data or the price of the oil vary in large amount or in small amount. What events will really have an impact on the that industry? Okay. So yeah, before just starting or directly getting to what Bayesian statistics is and why do we use the Bayesian theory and things like that, we might just cope up with those concepts. Of course, we are familiar with statistics, also distribution and sampling. So yeah, the distribution and in statistics, those are the common terms. The distributions, the samplings, and also the parameters. In which we're going to mention those words very um, repetitively after this, so maybe we might not be so that you might not be confused about it. So in distribution, we mean, for example, let's say we're doing a hypothesis or statistics for you to measure the height of people or the height of people in some area, for example. So yeah, that height or is there very large amount of number in with large height and small height. Those are the distribution of the data. So sampling in order to know the height or in order to calculate uh, the estimation, it might be hard or difficult to go through all the people or to measure all the people, so that we can take just sample of few people, so that who would we think that they will represent the whole society. And then there's the parameters, of course, which is the mean, the variance, the proportion, or any number of parameters that we want to estimate or that we want to know about that population. So there's this basic concept or the method, the statistics method that we all use randomly. It is called the frequentist approach. It is, maybe we're not familiar with the word, but it's the approach that we will use often. So this approach is classical way of doing statistics, which means it treats the parameters of statistical model as fixed but unknown quantities. Okay, so before starting the statistics or the hypothesis, we need to know or we need to have the first estimation or the first value estimation for those people, maybe for their height, maybe for their anything. Okay, so that value is called, we're going to take that value, fix it, but it is unknown. We're just going to put some hypothesis on that. So the primary focus is on the data collected through repeated sampling and how this data can be used to make inference about the parameters. So depending on the data, uh, then we're going to make an inference for those parameters. Okay, so it is just a statistical model. It is a fixed but unknown quantities for the mean, for the if the thing that or if the parameter that we're looking for is mean, that is that is it, or maybe the height or the standard deviations, the median. So we're going to take them as a fixed but unknown value. But on the Bayes theorem, yeah, the first one is before the Bayesian statistics. Yeah, it's used the term called Bayes, right? It's simply updating our prior intuition or intuitions about the parameter with information we gather from our sample, and then it becomes a question of how much do we weight our prior intuition versus how much do we weight the information we got from our sample. So it means that we might have a prior estimation or a prior analysis of this is the the like the hypothesis or the estimation that we have about this specific parameter, and then we're going to update that parameter depending on the new data or the new observation that we're going to have, which means it's simply updating our prior intuition about the parameter with information we gather from our sample. Okay, and then it becomes a question of how much are we going to depend on the data or on the observation, on the new observation that we have made, or which weights more. Okay, or the data or the analysis or the estimation that we already have or we get from our sample. Okay, so in the Bayesian theory, there is the P of data. So like now we have mentioned that there is the imagine the thing that we want to estimate is like a function. Okay, P of a slash data, which means on this, by this data we mean that the data that we have observed or the new observation, and a is the prior observation or the prior estimation that we have. Okay, which is P of data it is calculated this way. We're not supposed to know the details about the calculation, but it is just good to know the knowledge, right? So the concept, I mean. Yeah. So in this data, we mean that the data that depend the new data or the new observed data. Here it's the posterior. Yeah, overall PA slash data is called the posterior, which is the new distribution or that we're going to have after doing the Bayesian theorem. So P of data slash A, it's called the likelihood, which is we have observed or we have new observation of data, right? That we're going to update our parameters based on this data, right? So it's calculating that how much are we going to get, how much are we going to get. So yeah, doing this calculation, I mean, taking the parameter A, how likely are we going to get this value A or this parameter A in the data on the new data, okay? So which means how much are the new observation or the new parameter is going to be, what type of chance do we have to get this type of observation on the previous one. P of A is the prior observation that we have, and P of data, it's just normalizing constant that we're going to divide the whole this P of data slash A times P of A in order to normalizing to normalize the number, okay, making sure that our posterior distribution will sum to 1. So just this is just normalizing constant. So and the next is what is Monte Carlo or Monte Carlo Markov chain in CMC. So it's a class of algorithm. It's used to sample from probability distribution when direct sampling is difficult. So we're talking about here yeah, we're talking about sampling, right? We're going to have a sample in order to calculate our. So we've just said the Bayes theorem is about changing the parameters or updating the parameters, right? So we're going to have a sample or a data or an observation that we're going to update the parameters depending on, right? So here it's a class of algorithm used to sample from probability distribution when direct sampling is difficult. Okay, so there might be situations when direct sampling or taking just some data from the distribution will be difficult. So this method, they're particularly useful in Bayesian statistics to approximate the posterior distribution, or which is the end result of the Bayesian statistics or inference. So, what are the steps on Monte MCMC or Monte Carlo Markov chain? What are the steps? The first one is Monte Carlo simulation, and then there's the Markov chain. Then combining that, we will get the Monte Carlo Markov chain method. Okay, so the first one is it's a method of estimating numerical results by randomly sampling from a probability distribution. Okay, so imagine trying to estimate the area of an irregular shape by throwing darts at it. So by counting the number of darts that land inside the shape, you can estimate its area. So since the end result or the end goal is to just take some amount of samples or samples that will align that will be proportional with the posterior the posterior estimation or distribution that we're going to find out from the Bayesian theorem, we're going to take sampling from a probability distribution. And then, so the Monte Carlo or the first step is about taking numerical estimation by randomly sampling from a probability distribution. So from that probability distribution, or from that sample we get from the probability distribution, we'll be able to to estimate numerical results, such that maybe the parameters that we need. Yeah. So and then there's the Markov chain. What do the Markov chain will add on the Monte Carlo simulation is it's a sequence of events or states where the probability of each event depends only on the state attained in the previous event. So it is like working through a city, so which means that we already have some parameters that we have estimated or we have gained from the Monte Carlo estimation, right? From some samples or from randomly sampling from a priority distribution. Okay, so in the next step on the Markov chain, we're going to iterate through this process until we get some value that will be a better representative of the data or a better sample. Okay, so on this iteration, the second iteration will only depend on the first iteration or on the first step of in what that did it depend or what was the first result or what was the result from the first iteration. So the second iteration will depend on the first iteration. So it's a sequence of events or states, we can call them, where the probability of each event depends only on the state attained in the previous event. So the combining them, which is start like the NCMC method use the Markov chain to generate sample from the distribution, right? So like while combining the two steps, this is what we get. The first one is we'll start with an initial state and use a transition rule to move to a new state based on the current state. And then we'll repeat this process many times to create a chain of state. And these states are a sufficient number of iterations, approximate the desired distribution. So depending on the accuracy or the rules that we're going to assign in order to go from the first state to the second state, it will repeat itself for the iteration. So those two are the key concepts. Maybe if they're not clear. So the first one is involves using random sampling to solve problems that might be deterministic in principle, and it is used to estimate numerical results by performing repeated random sampling. And then the Markov chain is sequence of events or states where the probability of each event depend on the first one. So in Bayesian statics, there will be complex models where calculating the posterior distribution analytically is difficult or impossible. Okay, so here we can use the MCMC method. Uh, which will provide a way to approximate the posterior distribution, which is, as I said before, the distribution of the data that we're going to get after implementing the Bayesian distribution. We're going to get that type of distribution through just sampling. Okay. So we have understand the two, the Markov chain and the Monte Carlo, uh, the mixture of them, or why we will combine the two, right? So the end product is using those. We're going to make the Bayesian inference, right? So we're going to define the model, which is the prior distribution for the parameters and the likelihood of the observed data. And then there's the posterior distribution. There's this MCMC sampling or the algorithm, like there are different type of MCMC algorithms like the metropolis sampling or the give sampling, or if you use a library like the PCM3, you will just get it will sometimes can pick one of the algorithms by itself. And then which is the inference, which is generated samples to make inference about the parameters, such as estimating their mean, the variance, or the credible intervals. So just like doing or doing the MCMC, this is the method that we're going to follow, or the steps that we can follow, which is we've just mentioned it, but maybe in a using the key terms. The first one is initialization, which is starts with an initial value for the parameter, which is the parameters that we're going to estimate about, right? We've just said that on the frequentist method. Uh, yeah, we're going here. We've just mentioned that they are fixed, but they are unknown, right? But here we're going to estimate some value for them, and we'll start with those, taking those values as an initial value for the parameter. And then there's the transition, okay, which is we're going to use a transition rule. As we said, it's going to be an iteration, right? The second between the first iteration and the second iteration, right? So use a transition rule to move to a new value based on the current value. So the current value or the current value will have an impact on the second one. So the transition rule ensures that the Markov property is maintained, which is the character or the previous characters are going to have an effect or an impact on the second estimation that we're going to make. And then there's the acceptance, which determine whether to accept the new value based on certain criterion, which means we're going to keep iterating through that data, right? But are we going to take that sample or that output, which is the parameter again? Are we going to accept that or are we going to deny that? So we're going to put an acceptance which determine whether to accept the new value based on certain criteria. And this step ensures that the samples are from the desired distribution, or the samples that we're taking, or that the samples that we have are indicating the right distribution or are from the right distribution. And which is the other one is the iteration, which will repeat the transition and acceptance steps many times to create a chain of samples. Okay. So there are different type of common MC methods, as I mentioned before. The first one is the metropolis hasting algorithm, which will follow the steps that we have just mentioned, the new state, and then the acceptance ratio. It will compute the acceptance ratio, which is the ratio of the posterior probabilities of the new state in the current state and whether to accept or reject, and then repeats it. So in this part, maybe not to get confused about the posterior probabilities. We have these four states. The first one is the prior state, which is the estimation or the hypothesis that we already have about that data, or that we're going to alert by using the new data. Okay, and then there we have this the second. Uh, we have the new data, right? Which is and we're going to calculate the likelihood, which is if the data that we get or the new observation that we're getting is going to affect the first, it's going to be, similar with the data that we already have. And then there's the posterior probabilities, which is the end product or the final estimation that we're going to get, that we're going to do in order to get the distribution, which is called the posterior distributions. Uh, so yeah, let's go to some demonstration. So yeah, here we are going to make some um, demonstration for all the steps. So we can start from importing some libraries that are going to be useful for the estimation, which is NumPy and scipy.stats. So the first one is generate observed data. Um, so in this case, it's going to generate random data, or we're going to pick random data from just using, um, like in your case, you're going to put the values or the data that we already have, which is that the years in the price, right? So let's just use one variable here, which is x, and then we have generated a variable called x. Now, the thing that you need to note is we're going to put or alert our data depending on the new data that we had observed, right? So this is the new data that we have observed, or we're going to treat this data like that. So just defining the functions. The first one is the Gaussian posterior, which is x and theta. So also now we will try to integrate the knowledge that we have from the concepts to the code. Okay. So the first one is the first function will is defining the log likelihood and the prior. So we've just mentioned the two parameters, the two variables before on the note, right? Which is the log prior, which is this one, represents the log of the prior probability density function evaluated at theta. And the likelihood will define, yes, so the likelihood will define about here that we have the variable x, right? So what is the PDF, or what is uh, the value of the amount of, like, we have just an estimation called x, right? So we're going to put it on the data that we have already, on the previous observation or estimation, right? So how much is accepted, or how likely is the new variable called x, or the new data that is called x is going to merge itself with the previous one, or entering these two to the data. Let's say here look will implying the mean value and scale for the variance. So yeah, just putting those values or x on this mean and on this variance, and also on the normally distributed data, since we have just generated a normally distributed or Gaussian distribution data for x. So like putting them on x, how is that going to be accepted? That is the likelihood in the prior, and instead of x, we're going to put theta. Okay, so theta, just assume theta, since theta is a parameter, right? Now we're trying to, here we're taking theta index, so we're trying to estimate a parameter called theta, which is the mean here. So how likely is the theta going to fit on the previous data again, with this mean value and with this scale, which is the variance again. So the prior, or the log prior, it's used for that, in order to determine the acceptance. We need to keep the data or we need to, based on the previous data or the previous estimation, we're going to make the newly acceptance rate or acceptance of proposed parameters value during the sampling process. So the second function here, it's the Gaussian proposal, which is the theta, the Gaussian proposal taking theta, taking this parameter, which is here to indicate the current value for theta. Okay, so now we're going to estimate theta new, and it depends on, again, as we have said, it depends on the previous method, which is called the theta. Yeah, the theta current, or the current mean value that we have or that we're considering to have. We can change the scales. Also here we have the right to alert those values for the mean and for the, yeah, for the mean and for the scale. And then we have the 0.2 for the scale. Okay, so here yeah, yes, so let's just take this and return titanium, which is the new value or the new parameter for the new value. Okay, and then now we're defining another function called x1 comma x2. Now it's kind of comparing the two variables. Okay, which is calculate the proposal probability q of x2 slash x1 based on the Gaussian. Okay, we're going to return a value called q, so we can consider this q as a, as we have mentioned on the note, the value of how much are we going to take, no, like the yeah, the newly distribution that we're going to estimate from the Gaussian, from the Bayesian theorem. Okay, okay, so it's going to return q. So if we have large amount of q or large value for q, it means that it's more of, we're going to accept this parameter, or this parameter, or the new, this sample, or it's just an evidence that we're using the right or the good type of distribution, or for our sampling. So generating the new parameter based on the previous number. So our base here will indicate that the random variables, it just samples random variable from the distribution. Here we'll just use the random variable for the distribution, which will just generate random variable for the theta or for the newly proposed new value. So here we're going to compare two parameters, as we've just said before. So how much is going to affect the previous alteration or the previous result? How much is going to affect the new one? And finally, we're here, which is now this is, by the way, the manual form for applying the MCMC algorithm. We can just use the PYM3 MC3 library here. We're going to see that, but in order to understand the knowledge, so at the end, what this library will do is just merging all this process. Okay, now after just defining all the process, so we will just go through the all proposed yeah, we're going to go through all the proposed functions, which is all the process of all what we're going to. So there's this theta, there's that current value of theta, in that here the theta is going to be, if there is a new iteration, it's the newly estimated theta, or the newly theta value that we're estimating. Okay, so using the previous or the current, we can say that the current. So the new parameters, all new parameters, or all new estimations will depend on the previous one, as we have said. So those are the already the parameters that we have, and these are the parameters that we're going to estimate, and this will put the acceptance rate, or like it's going to say in how value are we going to take this new sample, or are we going to reject this new sample. So here we're saying there's this theta, which is the proposal function of theta current. The new function will depend on the current one, and this is the dependency on the data or the new data for the current probability and the new probability. So the acceptance ratio, if the estimation of the new one is greater than from the current one, then we're going to accept this value, and if not, we're going to just go iterating, and we're going to find for the value that will fulfill this situation. If acceptance probability is greater than the ST uniform, and again, this is the generated value or the randomly generated value, and then we're going to replace the data current with data new, and yeah, we're going to increase the acceptance. Yeah, just we can iterate like this, and we can implement the theorem on this way. But rather than doing this, we can just make them on a, yeah, here we're trying to see or visualize the output from this. So our output will be the mean value. It's all about the if we're calculating for the mean, or if the parameters that we're looking for is the mean, how is the mean value uh, being changed, or like how the previous one is altering the new. So is this iteration enough, or are we supposed to make another iteration? And those are the value that we're going to get from reading the graph. Okay, or just we can use we can remove this. Okay, so we might just use the PY library and see the library do all the steps. Here I have just mentioned the method or the algorithm that it is going to use, but as I told you, we might use we can just leave this, and it will choose what type of method will be appropriate for this method or for the MCMC method. But here we've just selected one. And yeah, by using the pure industry library as the p in those normal, here we're looking for the mean value, so we're adjusting the prior values or the data or the estimation that we already have. Again, you need to change those variables like mu and sigma. Okay, maybe sigma in this case, or scale, another variables too. We're going to adjust that in order to show the in order to indicate that this is my previous variables, or this is my previous distribution or estimation that I have in mind. And the new observation will be, we've observed in this case X, but if our observations include another parameters and another data, then we're going to include them here. So mu from prior, so we're going to depend for those parameters on the previous parameters. So yeah, and there is the step is we've just used Metropolis, and we're going to play the two plots, which is the trace plot and the plot poster. So in here we have got those two are indicating the trace plot, and the final one is the posterior plot. So the posterior plot will be the final plots that we're going to have. Since I have told you, or since we've been talking about what the posterior distribution is, the posterior plot will show us how the distribution is and how the new parameters are, what they look like on the new data. Okay, so here on the trace plot, it is going to show us the process, or while iterating through the data, how the iteration was. Okay, on the x-axis, we're going to see the iterations, or the number of iteration, and yeah, the number of iteration that it had gone through. And if we have see if those chains are following each other, then it means that, sorry, yeah, here it means that, I think it is visible now. Yeah, it means that they are they are continuous. Okay, they are the previous results and the new results, they are type of the same, or they're not that much varying with each other. It needs to get, which we can say that the iteration, or using this MCMC method, it's not covering very large amount of sample data, or it's not going to see a new value. Okay, the next iteration is not going to see that much new value if it keeps aligning with each other or with the previous one. So it needs to be, so if the chains, or if the relation between the lines are going to be a little bit different, so it means that it is discovering different type of data, sample data. But also it might be, if it gets through, it needs to be stationary at some point. Since they're going to be the same, the previous in the new one, they're going to be the same, since they both have reached, or they're going to keep getting the sample or the distribution that is going to indicate, or that is going to satisfy the acceptance ratio, or that is going to indicate the statistics or the distribution. So yeah, it needs to align, or it needs to be on same stationary point at some point. Okay, or it needs to be the same. The iteration are going to be the same. So the second one is going to plot posterior trace, which is this one. In this one, it's just going to plot what type of sample data do we have. Again, here we have the iteration, and here the mean values. Okay, so what type of data that we're going to, what type of distribution we're gaining from um, going through the samples. Okay, so in the first iteration, in the second, in the third. So this is our output result. So we expect this results to be convergent at the middle, which is to indicate that the mean value. If so, if it is, if we're using, for example, here we're using the normally distributed data from the beginning, so we expect many values or many numbers on the to be to converge or to be included on the mean part, right? Since we have just estimated a mean value of 3, if the mean is 3 over here, then we expect many of the values to be around this mean value. So we expect a convergent graph on for the plot posterior trace, which is like this. Yeah, in this way we can figure out, we can estimate different parameters uh, depending on the context that we're going to use or that we're going to follow. Uh, yeah, so thank you everyone. I will be sharing this code and the slide.